Okay, here's a second related rates trigonometry example. Before we get into it, let's review the steps we're going to use to solve this problem. First thing we're going to do is get a labeled diagram. And on that labeled diagram, we want to pay particular attention to which quantities are increasing and which are decreasing, because that's going to tell us what's the sign of each derivative. After that, we want to identify the known and unknown rates. Once we've done that, look at the variables in those known and unknown rates and get an equation that relates those variables. Lots of times that's the hardest part is getting an equation that relates the variables. Turns out that the calculus part of the problem is not that hard when we differentiate with respect to time. Sure, it involves a little technical skill, but it's not really the most complicated feature for a lot of friends. Then we want to solve for any unknowns using whatever skills we got. Let's get right into it. Two people are 50 feet apart. One of them starts walking north at a rate so that the angle shown in the diagram is changing at a constant rate of 0.01 radians per minute. At what rate is the distance between the two people changing when theta equals 1/2 of a radian? So we have the stationary person and the moving person. And I think what's implied here is that the moving person is moving on a path that's perpendicular to that horizontal base of the right triangle. So it's right triangle trigonometry is what we got going on here. Diagram is already labeled for us. X is the distance between the two people, and I'm pretty sure that the distance between the two people must be increasing since the person is walking away and the other person is not even moving. So there we have x as an increasing quantity. So its rate of change we expect to be positive. Identify the known and unknown rates. Well, we were told the rate at which the angle theta was changing. So that's a known rate. And then what we want is the distance between the two people is changing at a rate, and we want to find out what that is. So that's really about finding how far or how long is the quantity labeled x. So dx dt is the wanted rate. Taking a look at the tops of those rates, we see theta and x. And so we want to get an equation that relates theta and x. Turns out you got a couple of options here. So one thing you could do is you could use the cosine ratio and say the cosine of theta is equal to 50 over x. That's an equation that relates the two variables theta and x. But another person might observe too that the reciprocal of cosine is the secant, and the secant of theta is equal to x over 50, the reciprocal of the right-hand side we had before. Now, I'm going to work with the one on the right. So I'm going to take this cosine one and just set it aside. And I'm going to do this problem using this relationship. I don't have a real good reason to do that, but that's what I'm going to do. Okay, so now we just want to differentiate. And of course, we're taking the derivative of secant theta on the left-hand side, but we're understanding that theta is changing with time. So we're going to differentiate with respect to t for time. And then we have this variable theta. So we're going to use the chain rule. Of course, the derivative of secant theta with respect to theta is secant theta tangent theta. And then we have to multiply by the derivative of that inside function, that's d theta dt. On the right-hand side, we just have the constant 1 over 50 times x. And so the derivative is the constant times the derivative of x with respect to t. The derivative of x with respect to t is exactly what we want to get all by itself. Now, we were told that the angle theta was a half a radian at this particular moment in time. And so what we're going to do is we're just going to replace the d theta dt with its known value, and then we're going to replace theta with a half a radian. And then all we got to do is multiply both sides by 50, punch that into our calculator, and we get about 0.311 feet per minute. Here's a follow-up problem that's related to the previous problem. The figure shows a right triangle for which the leg adjacent to theta is fixed at 4 feet. The hypotenuse x is growing in such a way that the angle theta is increasing at a constant rate of 6 radians per hour. At what rate is x increasing when theta is 0.25 radians? So give a little bit of thought to that, and we'll take a look at the answer in just a few moments. Okay, the answer for that one, dx dt, worked out to be about 6.325 feet per hour. Thank you for watching.